Hey, this is the amateur logician. Thinking logically is to think more rationally, and also I would say more probabilistically, so to speak. Studying inductive logic sharpens our ability to assess probabilities and can even help us make better decisions. In this video, we'll briefly take a look at binomial probabilities via an example to build an intuition for the general formula. Consider tossing a coin. This is a Bernoulli trial, also known as a binomial trial, because it meets three standards. First, there are two possible outcomes for each trial, in this case, namely heads or tails, so we're good to go. Second, each trial is independent, so the outcome of one trial doesn't affect the outcome of another, so we're good to go. And finally, third, the probability of success is the same for each trial. In this case, we'll define success as coming up heads, so we're good to go. The question is, what's the probability that a fair coin will come up heads half the time in 10 tosses? We're going to think about this in a conceptual way. Now, one possible outcome in which half of the 10 trials come up heads might look like this. Heads, 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 and heads, and then just tails, 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 and tails. There's a 0.5 chance that we'll get that first heads. And then when we flip again, there's a 0.5 chance that we'll get a heads, and a 0.5 chance to get a heads, and so forth. But this right here is just one possible arrangement or permutation of an outcome in which half of the trials show up heads. But note that the order does not matter for this question. We don't care about the permutations, but the total combinations. The total combinations is 10, choose 5. Or in other words, we can first think about the permutations here. So we have 10 times 9 times 8 times 7 times 6. And then we want to get rid of the redundancies that are equivalent to each other because we don't want the number of permutations but the number of combinations. So let's divide that by 5 factorial. Or in other words, we have 10 choose 5, which is equal to 10 factorial over 10 minus 5 factorial times 5 factorial. So I'm going to erase this right here. So note that this here and this here are the same. That's the total number of combinations. But then we got to think about the probability. So we'll multiply that by that 0.5 chance, by that 0.5 chance, by that 0.5 chance, by that 0.5 chance, and that 0.5 chance. And I'm going to move this so that we have a little more room. So we'll multiply this by that 0.5, that 0.5 for that heads, that 0.5 for the heads, the 0.5, and that 0.5. Then we got to think about what's the probability of not getting the heads. So of not getting the heads, so that's going to be multiplied by 1 minus 0.5, 1 minus 0.5, 1 minus 0.5, 1 minus 0.5, and 1 minus 0.5. Or in other words, that's the same as we have that 10 factorial over the 10 minus 5 factorial times 5 factorial times the 0.5. So we have 1, 2, 3, 4, 5. So we have raised to the 5th power. And likewise with the 1 minus 0.5, that's raised to the 5th power. Throw that into a calculator, and we approximately get 0.246094, which is about 24.61%. So that is the probability such that a coin will come up heads exactly half the time in 10 tosses. I think this intuitively makes a lot of sense. I hope you agree. So if we think about the general formula for a binomial probability, we have the probability of big X equals little x is equal to n factorial over n minus x, that quantity, factorial, times x factorial times p raised to the x power times the quantity 1 minus p to the n minus x power, where x is equal to 0, 1, 2, etc. to n. So p refers to the probability of success, n refers to the number of trials, and x refers to the number of successes out of those trials. So if we consider our example, we have the probability of x equals 5, which is equal to 10 factorial, over 10 minus 5 factorial times 5 factorial times the 0.5 raised to the 5th power, and that's multiplied by the quantity 1 minus 0.5 raised to the 10 minus 5 power. Again, throw that into a calculator, we get about 0.246094. Now the point of this example, when we were getting this calculation here, was to try to build an intuition for our model, our equation, our general equation for binomial probability. Now, in previous videos, we've discussed the probability calculus and derived the conjunction rule, the disjunction rule, and the negation rule with the use of Kolmogorov axioms, and we've additionally discussed some combinatorics, which came in handy in this video, and previously we've even talked about the conjunction fallacy and the gambler's fallacy. If you want to see more videos on probability and induction, let me know in the comments below. I would appreciate that. In any case, thanks for your viewership. Good luck to you and be well.